Let's say that instead of a stationary circle, we start talking about circles that move, like car wheels or bicycle wheels or Ferris wheels, things like that. And let's say we have a point on the outside of the circle. If we spin this circle around, the point on the circle is going to pass through a certain number of degrees as it spins. And you know that as it spins in a complete circle, like so if it comes back to here, it will have gone 360 degrees or 2 pi radians. As a circular object rotates in a counterclockwise direction about its center, an object at the edge is going to move through an angle relative to its starting position known as its angular displacement or angle of rotation. And to figure out how many degrees or radians that a point has traveled through, we're going to multiply by either 360 degrees or 2 pi radians. So, we've done this before, we just didn't call it angular displacement. We talked about how many degrees an object would go through if a circular object spun a certain number of rotations. So in example 1, it says determine the angular displacement in radians of 8.7 revolutions, round to the nearest tenth. Now we're going to consider our revolutions to be counterclockwise in the positive direction. So in the previous unit, when we wanted to turn revolutions into angle measurement in degrees, we would multiply by 360. And we would find out that this was 3,132 degrees. But now we want to change this to radians, and we learned how to change degrees into radians by multiplying by pi over 180. So 3132 times pi over 180 is going to give you approximately 54.7 radians. However, there's a faster way of getting there because we know that 360 degrees is the same as 2 pi radians. So if you multiply 8.7 times 2 pi, remember, use the pi key in your calculator, you will still get 54.7 radians. In physics, one of the concepts we talked about was something called velocity. Velocity is like speed, but velocity had a speed and a direction. We called that direction and magnitude. So velocity, like if you're traveling 50 miles per hour south, it was a distance over time. Angular velocity is going to be a number of radians that a circular object goes through over time. The formula we're going to use is this. Omega is equal to theta over t. That's the lowercase omega. It looks like a W, but it's a little curvy. So theta is going to be in radians, and then the denominator is going to be time. So let's try this formula out. Number 2, determine the angular velocity of 5.8 revolutions are completed in 9 seconds, round to the nearest tenth. Okay, so the way this formula works is theta is the radian measure of your angle. So we first have to change 5.8 revolutions into radian measure. And we just learned that we can do that by multiplying by 2 pi. So 5.8 times 2 pi is going to give me about 36.44 radians. I guess I could have called it 36.4 radians because it wants me to work to the nearest tenth, but that's okay. And then we're going to divide that by the time, and the time is 9 seconds. So 36.44 divided by 9 is going to be about, I guess it's about 4.0. And the units of measurements are radians per second. Remember, Velocity is going to be in some unit of measurement divided by time. And our unit of measurement for this particular problem happens to be radians. Sometimes we don't want to know the final answer in the unit of measurement given. Sometimes we want to switch to a different unit of measurement. In chemistry, we talked about something called dimensional analysis. Dimensional analysis was a way of canceling out units of measurement that we don't want. So, in problem 3, a circular serving table in a buffet has a radius of 3 feet. It makes 2.5 revolutions per minute. Determine the angular velocity in radians per second of a bowl of peaches sitting on the serving table. I'm going to put a box around radians per second because that's the key to the end of the problem. So the first thing we do to find the angular velocity is we start by multiplying 2.5 revolutions times 2 pi radians, because there's 2 pi radians in 1 revolution. Well, the other thing is it said it was 2.5 revolutions per minute, so every 1 minute this happens. But we want to change minutes to seconds, so we're going to multiply by 1 minute over 60 seconds. So now what happens is these units of measurement cancel out. So I have to multiply 2.5 times 2 pi, and then I have to divide it by 60. When I do that, I'm going to get approximately, it doesn't tell me where to round to. So maybe we'll say it's 0.262 radians per second. The linear velocity is going to relate the distance around the outside of the circle that a point travels per unit of time. Well, the distance on the outside of the circle was called an arc length, and the variable we used for arc length was s. So the velocity is the arc length over time. Well, we said that arc length was radius times theta in radians. Wait a second, I just saw this a minute ago. Theta divided by t was the angular velocity. It turns out that the linear velocity can simply be found by multiplying the radius of the circular object by its angular velocity. Let's do an example of using the linear velocity. Determine the linear velocity of a point rotating at an angular velocity of 31 pi radians per second at a distance of 15 centimeters from the center of the rotating object. Round to the nearest tenth. This is just fancy talk for telling me that the radius is 15 centimeters. Because what's the distance from the center of the rotating object? Well, that's a radius. The linear velocity is the radius times the angular velocity. Well, the radius is 15 centimeters. And the angular velocity was 31 pi radians per second. When I multiply this all out, my final answer is going to be in centimeters per second. Remember, linear velocity is a distance over time, and the distance traveled is in centimeters. So 15 times 31 pi is going to give me 1,460.8 centimeters per second. In example 5, we're going to refer back to example 3 and use its data. In example 3, we found the angular velocity of a rotating buffet on a table, also known as a Lazy Susan, if you've never heard that before. We determined in example 3 that the angular velocity in radians per second was 0.262. Oops. There we go, radians per second. So the reason that I wrote that down is because now to finish off this problem, if a spoon is 1 foot from the center of the revolving table, in other words, if the radius is 1, and a fork is 2.5 feet from the center, the radius is 2.5, determine the linear velocity for each. So for the spoon, the linear velocity will be the radius times the angular speed, which is going to be 0.262, but it's going to be in feet per second. And for the fork, the angular or linear velocity is going to be 2.5 times the angular speed, which was 2.262, and that's going to be 0.655 feet per second. The last problem we're going to do is going to require us to do some dimensional analysis. The fastest human on a bicycle was John Howard, who achieved an incredible speed of 152.3 miles per hour in 1985. If the tires on John's bicycle have a diameter of 30 inches, and during a warm-up are turning at a rate of 141 revolutions per minute, determine the bicycle's speed in miles per hour. First of all, which speed are they looking for, angular or linear? If it says miles per hour, that means they are looking for linear speed. So the linear speed is r times omega, which is r times theta over t. Because we don't know what theta is yet. They just told us that it's 141 revolutions per minute. We're going to have to change that into radians per minute. The radius is 15 inches because they told me the diameter was 30 inches. But they want the final answer to be in miles per hour. If I do the problem as is, the answer is going to be in inches per minute. So we're going to start by doing 15 inches. We're going to multiply that by 141 revolutions per minute. And then we're going to also multiply that by 2 pi radians, so that's going to change revolutions into radians. And to just kind of help us out, I'm going to start by multiplying this together, because otherwise there's a lot of stuff going on in the dimensional analysis, so I'd rather break it up a little bit. So I'm going to call this 13,289, and then it's going to be inches per minute. Now we're going to worry about changing inches per minute into miles per hour. So 13,289 inches per minute. The easy part is changing minutes into hours because there are 60 minutes in 1 hour. So I'm going to put 60 minutes over 1 hour, so that'll get rid of my minutes. Now the fun part is changing inches into miles. How many inches are in a mile? Well, you may not remember this, but there are 5,280 feet in 1 mile. So if there are 5,280 feet in a mile, and there are 12 inches in 1 foot, I can find the number of inches in a mile by multiplying 5280 times 12. 5280 times 12 is 63,360 inches. Now that will get rid of this, and when I'm done multiplying this out, I'll be left with miles per hour. So I'm going to do 13,289. I'm going to multiply that by 60, and then multiply by 1, but that doesn't do anything. Then I'm going to divide it by 63,360, and I'm going to find out that it's about 12.6 miles per hour. And that is linear and angular velocity.